Hello, everyone. Can you guys hear me? All right, good. This is a 10th lecture of CS292F Convex optimization. And we're going to be continuing our journey on duality and primal and dual. And then today we're going to be talking about duality and the optimality conditions of the general convex optimization form called KKT conditions. Okay, the quick logistic note is that the homework 3 is posted you can find it on the link from Piazza, and then it's going to link you to the Google Drive box, and on there you will find the document for the third homework and the corresponding data the data set for you to work on the coding questions. Okay, so please start early and don't wait until the last minute. There are two small pieces of coding that's required for this homework. So if it is a holding that's holding you guys up, that's taking most of the time, definitely start early. Okay, so it's gonna cover until the end of the lecture on next Wednesday, and then you will have the full 2 weeks to do it. Yes, so there's a question, a clarification question regarding homework 3. So you only need to do either question 1 or question 2. So you can choose between these two and to just do one of them. And then the total credits that you're going to be getting is going to be the question that we grade on question 1 and question 2, and together with the credits that you get for everything else. Okay, I hope that's clear. Okay, looks like we have most people that's coming to the lecture. So let's get this lecture started. So last time we talked about duality, and we consider this optimization problem of the following form that's not necessarily a convex optimization problem, with objective functions, inequality constraints, and equality constraints. Okay, so this is fully general. And then to derive the dual of this optimization problem, we follow this very mechanical steps. First, we define something called the Lagrangian by lifting the constraints up to the objective functions with affine terms and introducing this U variable and V variable called Lagrange multipliers. Okay, so let's apply each Lagrange multipliers to one of the constraints, and then the functions in this constraint, and add everything up. So first convert everything into this general minimization problem, construct the Lagrangian, and then getting rid of this primal variable x by taking the minimization, and then it becomes a function of only the Lagrange multipliers u and v. So that would give us the so-called Lagrange dual function. Okay, so the Lagrange dual function would be the function to maximize in the dual optimization problem of this form. So the only requirement, the only natural constraint that comes into the dual problem is that this U parameter needs to be non-negative. It's important to note that even though the primal problem might not be a convex optimization problem, the dual problem is always a convex optimization problem, using the fact that the construction of G is a pointwise maximum. Moreover, for all pairs of primal and dual optimization problems, we have the primal and dual optimal objective criteria, and they always satisfy the so-called weak duality, which says that the primal minimum is always larger than the dual maximum. And in addition, for convex optimization problems, under a very general condition called Slater's condition, so this is one of the constraint quantification conditions. So this is among the most popular, that there exists, provided that there exists an X that lives in the strict interior of the set of constraints, of the set of inequality constraints, then then we say that strong duality hold, in which case we can equate F star and G star. Okay, and this can be further refined such that the strict inequality only needs to hold for all these non-affine inequality constraint H1 to Hm. For the part of the inequality constraints where H is actually an affine function, then we don't actually need a strict inequality. And this implies that for the family of linear programs, provided that the solution exists, then the strong duality is always true. Okay, so today we're going to continue on the discussion of the primal and dual. In particular, we're going to be talking about the following topics. We'll talk about the KKT conditions, which is a general characterization of the set of primal and dual optimal solutions for problems that satisfy strong duality. And then we're going to give several examples on KKT conditions just to illustrate how useful it is for us to gain insight about optimization problems. So then we'll talk about how do we use duality and KKT conditions for a number of applications. And so this lecture will consist of talking about the general condition, and then talking about many examples of application of these conditions. Okay, so are you guys hearing the noise? I think someone is like trimming the tree or something, like might be our neighbor. So I have to go and close the window and come back. Oh, you can't hear it. That's good, but I can hear it. So just give me 5 seconds. I'll go and close the window. It's really annoying. I can hear a little bit of it, but yeah, after closing the window, it's a lot better. Okay, so this is outline of today's lecture. So let's get to it. So first, so we'll still be considering the general optimization problem without assuming that this is a convex optimization problem. And the set of conditions that characterizes the set of optimal solutions is the so-called Karush-Kuhn-Tucker conditions. Okay, so we have 4 components, and that's very easy to remember. So the first thing is the so-called stationarity. So this says that I guess a triplet, the triplet X, U, and V satisfy the so-called stationarity condition in which 0 is in the subgradient of the Lagrangian. Okay, so this is a condition that's equivalent to say that X is in the arc mean of the Lagrangian. Given by this input points U and V. Okay, and the second condition is so-called complementary slackness. This is a more interesting one. So this is saying that the primal and dual variable needs to satisfy this condition for the inequality constraints, which says that either notice that this UI is always non-negative. So either UI is 0 and HI is strictly negative, or UI is or UI is strictly positive. If UI is strictly positive, and that implies that HIX needs to be 0, meaning that the inequality constraints is actually active. Okay, and And then there's this standard feasibility condition, which says that, well, this is an optimal solution, therefore it needs to be feasible. So these are like more well expected. Okay, so if you think about the KKT condition, it's really just a more explicit way of rewriting the subgradient optimality condition for the constraint optimization problem. Okay, let's take a closer look at this KKT condition and see like how it actually gives us a characterization of the set of optimal solutions. First, let's consider working out this set of inequalities. So let's maybe first consider the direction of showing the necessity of KKT condition, saying that if X star, U star, and V star are solutions, are optimal solutions. And in addition, let's assume that we have zero duality gap. Okay, then it follows that this system of equation, first of all, this follows from strong duality. Okay, and then by the definition of G, which is the pointwise minimum, we can which is a pointwise minimum of this affine functions, and we can just write it out, right? And that gives this by definition of GUV. Okay, and then the next inequality uses the fact that that this is the minimum. Therefore, if we substitute any specific value x into here, then we get something that's a valid upper bound. Okay, by the optimality. And finally, using using the fact that this is always smaller than 0, then we can simply drop that and then upper bound this with simply f star. Okay, so why is this always, or why is this always 0? So well, this is by construction, by the feasibility condition that ui star is always non-negative, and also by the feasibility condition of xi, which says that this is 0 and this is non-negative, and this is non-positive, right? Therefore, the whole thing is smaller than 0. What this is basically says is that everything in this system of inequality actually satisfy everything is equal. Okay, so what does it say about KKT condition? So it turns out that we can get KKT condition directly from this derivation. So so to begin with, notice that from the previous derivation, we know that the point f star actually also minimizes this L x u star and the v star. Okay, so that's essentially like stationarity condition. So to see that, so notice that this f x star is equal to mean of x f x plus all the other things, that is L x u star and v star. Therefore, f star is a minimum, and this is equivalent to 0 is inside the subdifferential of x u star v star, right? And secondly, notice that for this to hold, we must actually have this non-positive term to be exactly 0. And for this to be true, notice that over the summand, so every individual ui star, hi, x star are each one of them is actually non-positive. Therefore, in order for the sum to be 0, we need every individual one of them to be 0. And that gives us exactly the complementary slackness. Okay, so and then the feasibility conditions are trivially true since we are assuming that this u star, v star, and the x star are the optimal solutions to begin with. Okay, so that checks all the conditions in the set of KKT conditions. Okay, so notice that we are not making any assumptions about the convexity of the optimization problem. So this is fully general, but we are making a very strong assumption on the fact that the duality gap is actually 0. So now let's look at the converse. Let's look at the sufficiency part of the KKT condition. And KKT condition, anything that satisfies the KKT condition implies that this set of solutions X star is the optimal solution for the primal, and U star V star are the optimal solution for the dual. Okay, so let's try to see this. First of all, we can just by definition write down definition of G. We can write we can write this down with an additional difference being that this is a minimum, right? This is a minimum of over X. But then this is equal to by just substituting this F star inside it using and stationarity. Okay, first apply the definition and then use the fact that X star is the one that attains the minimum. And by applying the assumption of the first KKT condition. And now by applying the complementary slackness, we can see that this is actually 0. And this is 0 by feasibility. By the feasibility condition. And then that gives us the dual solution is equal to the primal solution, which gives us that the duality gap is actually 0. Okay, and since the duality gap is actually 0, and for any feasible solution, then G UV is a lower bound of Fx star, and this X star actually attains this lower bound, that certifies that by the definition of optimality that X star is optimal for the primal. Similarly, since Fx star is an upper bound of the dual optimization problem for any UMV, and this pair of U star V star actually attains the maximum, and that implies that U star and V star are optimal for the dual problem. Okay. So to put the both side of the equations together, then we can conclude that the KKT conditions are always sufficient to certify that this triplets of solutions are optimal, and it is also necessary if we in addition assume that strong duality is true. Yeah, to put it together, we can get a statement that looks like this. Okay, so given that for the family of convex optimization problems, strong duality is relatively easy to check, and then for the subset of problem that's covered under KKT condition that's convex, then we can more or less say that the KKT condition is a sufficient and necessary condition to characterize the set of all optimal solutions. So I'd like to say that the version of the KKT condition that I'm presenting here uses subgradient, and the point of view is coming from the Rockefeller book, and you might have seen like other versions of KKT condition, even though they have the same name. Other versions of KKT condition that uses gradient rather than the subgradient, and those versions of KKT conditions might have a different kind of conclusion in terms of sufficiency necessary of certifying optimality. So just take that in mind, because this version of KKT condition deals with a global optimal solution. It doesn't really worry about local optimal solution or stationary points at all. There are versions of the KKT condition that deals with the problems of finding all critical points or stationary points that uses gradient instead of subgradient. Those are a different kind of creatures than the one that we are presenting here. So for the purpose of this class, we'll be sticking to our definition here. Since we focus mostly on convex optimization problems, and we mostly consider and we often need to address the problems that are non-differentiable. Okay. So another thing I wanted to say about the KKT condition, just a little bit of anecdote, is where it's getting its name from. So what happened is the following. So Hu and Tucker are mathematicians who contributed significantly to the development of the convex analysis. So they discovered this condition in 1951, and then after their works published, they later found out that some Indian guy whose name is Karush have already previously published the exact versions of this set of conditions in his master's thesis, like 12 years before the Kuhn-Tucker condition. So after the discovery later, they to honor Karush, they added another K, so now it's called KKT condition. So in some older textbooks, you'll still see the reference to these conditions by the Kuhn-Tucker condition rather than KKT condition. Okay, so in the hindsight, it's not intuitive. It's not really surprising that this conditions discovered multiple times in the history. So there's a law called the Stigler's law, which says that if some mathematical fact is named after a particular person, then with high probability that person is not really the original inventor or the original discoverer of this fact. So in general, it's not surprising, but for the KKT condition itself, you can basically just get it from the definition of the subgradient and stated in the less transparent way using the normal cone. Notice that we can always cast the convex optimization problem as unconstrained problem with indicator functions, and then by just doing that and then use the subgradient optimality conditions, then we can already get the KKT condition. But I wanted to emphasize that the importance of having something that's more explicitly stated in a set of 4 conditions than this, because this is like not really this is not really useful for many purposes. And suppose we have the 4 conditions that we can check, then it becomes a lot more easily applicable to some of the problems we'll see in the next couple of slides. Okay, so let's start by giving a few examples of the KKT condition to illustrate the point. So let's consider the QP. So this is a quadratic optimization problem with a convex quadratic function to minimize, subject to an affine constraints. Okay. What is the optimal solution here? So we already know that we can write the optimal solution, characterize the optimal solution using the Lagrange multiplier approach. So let's now try to use a KKT condition. Okay, we first write down the Lagrangian very mechanically by adding this additional Lagrange multiplier U. So this is half X transpose Q X plus C transpose X, and then plus U transpose A X, right? And then the stationarity condition would say that since this is differentiable and convex, then it becomes a gradient of XU, the partial gradient of the Lagrangian equal to Q of X plus C plus A transpose U. This is equal to 0. Okay, and then by the feasibility, we have another equation which says that AX is equal to u, 0, right? So this gives a system of linear equations with respect to x and u. So if we vectorize x and u and put them together, just stack them up, then we can rewrite this linear system of equation as qx times a transpose u is equal to minus c, and ax is equal to multiply plus 0 times u is equal to u. And that gives us this very cleanly looking system of linear equations. In other words, like a linear constraint version of the QP is very easily solvable by simply solving a system of linear equations. Okay. So in this case, like since we don't have inequality constraints, we don't need to worry about complementary slackness or anything like that. Okay. So let's give another example on support vector machine. Okay. So so this is a problem that we have considered multiple times already. So let's use the new tools that we learned, KT conditions, and write down let's write down the set of optimality condition for this. So first of all, let's again write down the Lagrangian. So the Lagrangian it consists of the primal variables. So we have 3 primal variables here, and let's add the 2 dual variables. Let's add the 2 dual variables u and v correspond to u in R to the n and v in R to the n correspond to the 2 inequality constraints. And in order to do that, we need to make this a standard form, which involves making this minus psi I smaller than 0, and I guess 1 minus psi I minus yi x I transpose beta plus beta 0 being smaller than 0, and then we multiply this ui and psi I on ui and vi on both sides of the equation. Okay, so it will be u and v. So the Lagrangian would look like beta square plus c I from 1 to n psi I and plus u transpose okay, yeah, I think he used v and w, so let's adhere to that notation, and instead of using u, let's call this let's call this v, and let's call this w. Okay. Then we have v transpose psi, we transpose, I guess, minus psi as a vector, and then we'll add the last variable corresponding to last set of inequalities, which gives us the sum of wi 1 minus psi I minus yi xi transpose beta plus beta 0. Okay, so that gives us the Lagrangian. Okay, and then the stationarity conditions involves, since this is differentiable, involves taking the gradient of the primal variables and assign it to 0. So let's take the gradient of this Lagrangian with respect to the different primal variables. So first of all, let's take this with respect to beta 0 and take the partial gradient with respect to beta 0. It only appears in the last term, right? So so we end up getting sum of wi yi I from 1 to n is equal to 0. Okay, so that gives us the first condition, and let's take the partial gradient with respect to beta as a vector, right? So the coefficients is not the offset. So we'll first get beta, and then plus sum of wi yi in fact, minus yi and xi. Okay, so minus yi, so I'm making this minus. And this is equal to 0, and which implies that beta is equal to moving the whole thing to the other side. So notice that this xi is a vector here of the same dimension as beta. And lastly, let's take the partial gradient with respect to Kasai. Notice that Kasai appear only in the in many of the terms. So we get let's maybe take it with respect to just one coordinate of this, which gives us c plus vi and minus wi. Okay, and this setting this to be 0 gives us that w needs to satisfy w equals to c vector 1 and minus this v vector. Okay, so all these are coming from stationarity. So then by the complementary slackness, since both of these set of inequalities are both this set of inequalities are not affine, not equalities, they are inequalities. So we now can use the complementary slackness. So the one that associated with this set of constraints is vi cos I is equal to 0. And then the other set is wi multiplied with everything here is equal to 0. Okay. So this gives us a set of KKT conditions. And what does it say? I argue that they actually tell us something that's very meaningful about the optimal solution. Okay, so let's take a note. So first of all, this condition, then beta is equal to these, allows us to reconstruct the optimal primal optimal solution using just a dual. Okay, suppose you manage to find the dual optimal solution by solving the dual, and now you have this wi parameters. Then you can already reconstruct what this primal coefficient vector beta looks like. Okay, so you get to implement this in your homework, and also derive the procedure to construct the beta 0 from the optimal dual. And by the complementary complementary slackness, so by this complementary slackness condition, we know that the wi is 0 only if like this inequality is actually active, meaning that this inequality is true at this set of optimal solutions with equal sign. Okay. So that's essentially selecting the data points that contributes to the final solution of the optimization problem. So when these wi's are 0, then those data points, it doesn't really matter whether those data points are there or not there. It's not going to affect your optimal solution at all. Okay, but for those where this wi is actually non-zero, so we call them the support points or support vectors. So that's where the name support vector machine is coming from. Specifically, let's maybe parse this equation a little bit. So xi transpose beta plus beta 0. So this is the decision boundary that we are going to decide whether the model parameterized by beta and beta 0 is going to predict positive label or negative label. Okay, so that's this hyperplane. Okay, so on one side of this hyperplane, we're going to predict green. On the other side of the hyperplane, we're going to predict red, or plus or minus. Okay, so now suppose Kasai is 0. Suppose Kasai is 0. So notice that Kasai being 0 is mandated by this complementary slackness. Okay, So suppose psi is 0. This means that we suppose psi is 0, then this means that the data point actually sits right at the so-called margin. So so these two lines are margin. Okay, if you shift the decision boundary a little bit towards one direction by a distance of 1 over beta's norm. Okay, so that's given by x transpose beta plus beta 0 is equal to 1, and x transpose beta plus beta 0 is equal to -1. Okay, these are given by these hyperplane. And epsilon psi equals to 0 says that xi sits right on this edge of margin. Okay, and also this wi parameter, this alternative, this other dual variable is actually strictly positive by complementary slackness. Moreover, like there are other support points where this psi I is not equal to 0, and these are the support points where like your model is making the wrong prediction. Okay, so if xi lies on the wrong side of the margin, and then you can directly read it off from this parameter psi. Okay, so so I hope that this is like informative, especially for those who have seen support vector machine but have never inspected it geometrically. I hope this is meaningful. And also notice that since this margin is on the so this is 1 over beta squared. That's why adding a regularization term in terms of beta square in the original SVM is called the max margin classifiers. So the business of max margin classifiers, max margin Markov networks, max margin everything, like used to be like something that's as popular as deep learning today. Okay, so notice that from KKT condition we can read off a lot of the structures of the optimal solution, although it doesn't really give us a way or a more efficient way of finding the optimal solution, but it leads to better understanding. So in particular, the sparsity of the support vectors, since a lot of these WIs are non-zero, tells us that maybe we can get rid of a lot of those data points that's not very much relevant to the purpose of finding linear classifiers, and that helps people to develop algorithms that screen out or actively select data points to obtain labels. Right. So notice that notice that from the condition itself, it can give us something called screening rules that allows us to not collecting labels for those data points that would otherwise be have no meaning in obtaining the optimal solution anyways. Okay, so another way of thinking about it, about support vectors, is that what is a minimum set of data points that you can use to teach the machine to learn this true beta parameters in the most efficient way possible, and that's related to the line of research called machine teaching, where you want to actively construct a set of points that allow machines to learn. Okay. So the next thing that I want to talk about is the constrained and Lagrange forms of optimization problems. So we often see this when we deal with say regularized or penalized optimization problems. And then in particular for lasso that we've seen many times. So sometimes this H is a one norm smaller than T, as in the 1996 paper by Rob Tipshirani. And then the more popular version of the lasso deals with the regularized version, which penalizes the one norm to induce sparsity rather than setting the allowable size of the one norm, like a priori. Okay, so people often claim that these two forms are equivalent to each other for convex optimization problems. So before we learn the KKT conditions and duality, it's not really clear like how do we formally establish that they are actually equal. But now we can. Okay. So first of all, we can say that maybe there exists a lambda parameter for every t that we can construct such that the solutions are identical. Okay. So let's assume that if problem C is strictly feasible, which gives us a strong duality by Slater's condition, and then then we know that by the KKT condition that there exists some dual variable, right? If you construct the Lagrangian, then there's a dual variable that got multiplied into this hx. Okay, so there's some dual variable such that the optimal solution of this is actually a minimizer of the Lagrangian. But the arc mean of this is equal to the arc mean of f of x plus lambda h of x. Therefore, the dual optimal solution is actually how we can directly construct the equivalent Lagrange form optimization problem. Okay, so we can also do the same from L to C, right? So we can do this by we can do this by applying the KKT condition, right? So what is the KKT condition here? It basically says that 0 is in the subgradient of f of x plus lambda of h of x, right? For the optimal solution of C. But what is it saying? This is saying that the pair of solutions x and lambda actually checks the KKT condition of the constrained version of the checks the of the constrained version of the problem. If we take t to be simply h of x star, right? This lambda is non-zero, and then check the KKT condition is true because this inequality is actually true. Okay, so we can construct the a problem in the constraint form from the solution in the Lagrange form as well. So in conclusion, we have shown that the family of solutions as we change lambda, like is always a subset of the solution that's in the Lagrangian form, and in the constraint form, and the converse is also true, provided that we assume that T is chosen such that the problem is strictly feasible, which is almost always. Okay, so let's do another example on lasso. Okay, and let's think about the theoretical problem of support recovery. So we've been talking about how the one norm is a tightest convex relaxation of L0 norm, which counts the number of non-zero elements in beta. So the latter is a very difficult problem. It's a NP complete problem for solving. But like maybe we can solve lasso and obtain the very sparse solution. And how do we formalize it? How do we show that under some reasonable model under which the true solution is sparse, and how can we prove that the optimal solution that comes out of lasso actually have the properties that it recovers all the correct it doesn't make any false positives. Basically, it says that any solutions that are non-zero in the optimal solution is actually also non-zero in the original input. And sparsistency is something that's even stronger, that says that these two sets are equal. Okay, so so let's see how we can solve this problem by simply using by simply using the KKT condition. Okay, so let's like maybe derive the let's maybe derive the KKT condition. So so first of all, like maybe we need to do a reparameterization of this problem. So we have mean of beta, and let's add a dummy variable called u, x beta minus y square plus lambda of u, 1 subject to u is equal to beta. Okay, so this is a trivial reformulation of the problem, so that we can decouple the two terms, and then we can derive the Lagrangian of beta u and the dual parameter v. So this is equal to half x beta minus y square plus lambda u 1 plus v transpose u minus beta. Okay, and then by the stationarity condition, we take the gradient with respect to beta and u and assign it to 0. And now it decouples, so it becomes relatively easy. We can work out the gradient, and the gradient is x beta minus y is equal to v, and this is a gradient equals to I guess equals to v, since we're minus beta here, and the second condition is that when we the subgradient, the lambda multiplies the subgradient of u1 contains the gradient contains minus v. Okay, so these are the set of stationarity condition, and we don't have complementary slackness since this is equality constraint. By collecting these two conditions, and we can actually eliminate one of the variable, and then that gives us this more compact representation of the KKT condition. Yeah, sorry, I think I missed something. So when I take the gradient, I missed this x transpose. Okay, this is x transpose x beta minus y is equal to v, and then we have this subgradient, and the subgradient of the 1 norm, like we know what it is. It's simply the sign when u is strictly positive or strictly negative, and anything between 0 and 1 when u is 0. Okay, so that gives rise to this set of two conditions. And we can actually just prove sparsistency and at least prove the no false discovery using just the KKT condition. So how do we do that? It requires us to construct a pair of solutions, beta star and v stars, such that and then we can check that this set of solutions satisfy the KKT condition. If we can do that, and then the construction actually satisfies that the sparsistency condition, and that leads to a formal proof that the optimal solutions also satisfy that condition. So how do we construct that? So a typical approach is to construct that using optimization as well. So we can consider the so-called fictitious optimization problem that looks at all these variables in the feature in the data matrix that correspond to only the non-zero elements. So let's call this set of S the support set, and then optimize only over the support set. Okay, so this problem is fictitious because you can't really solve it, but we don't really need to solve it. All we want to do is to somehow construct the existence of a solution and show its property. And naturally, the optimal solution, let's call it beta star of S, satisfy that the no false discovery. So any non-zero elements, because all of the beta star S correspond to coordinates where where it is non-zero in the generating coefficient beta 0. Okay, so we can construct a candidate primal solution by beta star, and then just padding all those non-zero and padding all those other coordinates with 0. Okay, so it suffices to show that this solution is also optimal for the original problem when we do not make it fictitious. So to do that, it suffices for us to construct a dual solution like V star and then check the KKT conditions. And what is a candidate dual solution? We can in fact just do the same trick and then find the dual optimization problem for this, and then that corresponding dual solution will have like more or less the same will have more or less the same same kind of properties as the one that we need previously. So let's like if we do that and then make and then like somehow check this condition after we plug in beta s star, padded beta s star, and then also plug in the constructed V star. And if this condition and that condition are true, then we can basically say that the null force discovery is proven. And if we can, in addition, show that for all the coordinates they hold with strict inequality, then that gives us a sparsistency. So notice that this is where you start to make assumptions about how the data is generated. So under this data generating distribution, then and using the fact that of the distributional property of this normal random variable, so that's something that you can clearly establish. So we'll do a little bit of it. So let's try plugging in this padded beta star s into the first equation. So without loss of generality, we can write it as beta xs beta s star minus y x transpose. And we know that when if this is the optimal solution, then it satisfies the KKT condition, and then we actually based on this we simply already get a candidate solution without using the without constructing the dual for the fictitious, right? So this is a corresponding solution called V tilde that correspond to the primal solution beta s star. It's not hard to check that this one is feasible. Now it suffices for us to check whether the Vi tilde corresponding to those i's that are not in S, and see whether this Vi tilde absolute value is strictly it's strictly smaller than 1. Okay, and we can already see that to establish how this one could possibly be strictly smaller than 1, it suffices to show that under the model, this beta s star is actually giving us a very good estimate of this y. And then since we know that y is equal to xs beta 0 plus noise, then it remains for us to bound the magnitude of the noise as its inner product with all the other coordinates in this matrix X. Okay, so I'll stop here. So this is how you can prove support recovery, and using a very similar argument, you can prove the rank recovery in matrix completion problems and in robust PCA and so on. And everything simply relies on the KKT condition. And the good news about the KKT condition is that there are just 4 conditions out there. So there are limited combinations of the algebra that you can work out. And the creative part of this procedure is really how do you construct a set of candidate solutions that are reasonable, and then you can then go ahead and check the conditions. Okay, so we'll take a break, and then in 2:03 we'll resume and then talk about other applications of duality and KKT conditions. Yeah, meanwhile, if you have questions that you want to ask, please post them in a group chat, and I'll respond to that once we resume. Okay, let's resume the lecture. So I didn't see any questions, so I'll just continue with the lecture. All right. So let's come back to duality, right? So we talk about two different uses of duality from the previous lecture. Um, so first of all, duality is very useful for us to determine a stopping condition um, when we are using iterative methods such as gradient descent or stochastic gradient descent to determine how close that we are from the optimal solution. Okay, so we already know that that in our like programming part of the assignment, then that in order to plot a nicely looking figure, like you need to somehow know what this f x star is with very high numerical precision. But in practice, like we never really know like how small this optimal solution is, except like very specialized cases. And the point is that we can actually upper bound this with any fx and any pair of feasible u and v. Specifically, so notice that what KKT condition is giving us. Sometimes it's giving us a relationship of u, v, and x for us to use one to construct another. So remember in support vector machine, we know that this beta can be constructed using the dual variables, and that's what you can naturally map this x into a pair of variables in the dual space. They don't need to be necessary. Sorry, they don't need to be optimal, but they can be constructed as a function of x. So by doing that, then we can simply calculate the duality gap as a certificate of the suboptimality gap. Another application of duality is that um, um, whenever strong duality is true, then we can then we can actually solve a different optimization problem, and sometimes the dual problem is easier than the primal, right? Then we can simply solve the dual and then reconstruct the solution of the primal. So uh, let's talk about that a little bit more. So consider this general optimization problem. We know that the Lagrangian looks like the following, and then the stationarity condition satisfied uh, by the subgradient optimality condition, then we simply we know that we can simply write this down like on the uh, maybe another regularity condition that the subgradient operator um, um, decomposes over the subgradient of the different functions, and often like the solution of this problem gives a very explicit characterization of the set of optimal solutions. And if we can directly solve this equation, and then we can obtain the primal optimal solution x star and the dual optimal solution u star. Very much like this constrained equality constrained quadratic optimization problem that we have seen before. Okay, and well. So let's give an example of one specific case where the where the dual problem is actually much simpler than the primal, and in which case we can solve it orders of magnitude faster than suppose we have to solve the primal directly. Maybe there are also additional system benefits of doing this that allows us to solve this in the distributed machine in parallel or so on. Okay, so let's consider this problem where the objective function decomposes. So it decomposes into fi's, but moreover, it also decomposes across a coordinate. So the parameters decomposes uh, can be partitioned into x1 to xn. Okay, and we want to solve this subject to a equality constraint. So notice that this problem, suppose we do not have this constraint, then this problem is trivially solvable. We can basically minimize fi at different I separately, right? But this equality constraint couples everything together. Okay. Now let's construct the dual problem by first constructing the Lagrangian. Okay, so this is Lagrangian, and then we want to get rid of variable x by minimizing it. And then we know that when we minimize it, since this is a linear constraint, so this becomes bi. So this becomes the v sum of bi minus ai and xi. Okay, and this is saying that we can actually just minimize everything individually by finding each x individually, and notice that this is by definition the whole thing by definition is a negative potential conjugate, right? So if we know the conjugate of this fi function, we get this fi star, and then we substitute this arguments into the Finch conjugate, and that gives us the dual objective function to maximize. Okay. So the dual form is an unconstrained optimization problem that maximizes over just a single variable v. Right. So this becomes a univariate optimization problem. It is also by the property of the duality, the dual problem is always a convex optimization problem. Therefore, it becomes very easy to solve because it doesn't involve any addition. The challenges are coming from the dimension. You can even solve this with bisection. And now, once we obtain the optimal solution V star, then we can very easily reconstruct the optimal solution X star by solving this problem, right? So once we have V, we can simply solve this problem. Notice that the solution to this problem actually decomposes. So essentially, after we figure out what this optimal V star is, we essentially have gotten rid of the constraint, so everything becomes decomposable, right? And this allows us to solve each one of these problems in each local machine by after passing this optimal V star to each individual data point. And in addition, each one of them is just a univariate optimization problem, and it simply involves solving a simple convex optimization problem locally. That's univariate. Again, we can do that by bisection. So in total, the computational complexity of solving this have reduced from having to solve an n-dimensional optimization problem to solving n one-dimensional problems separately. Okay. So let's continue. So we talk about dual norms. We talk about if you have one norm, and then you can construct the dual norm by this definition. Okay, and this naturally gives us the Holder's inequality, saying that the Z transpose X is smaller than any decomposition of the two different norms. So this is a generalization of a Cauchy-Schwarz inequality, and we often use this to get like slightly tighter bound that depends on depends more favorably the dimension of the problem. Okay, so so you guys still remember this, right? So we we did the calculation for the LP norm when P is between 1 to infinity. And we also talked about the matrix version of these norms and argued that the trace norm or nuclear norm, which is the sum of the singular value of the matrix input X, is the operator norm, which corresponds to the largest singular value of X. Okay. So another property that we talked about back then was that the dual of the dual norm gives you back the original norm. Okay, so this is an interesting property that we have seen from an alternative approach by just directly proving that like by definition. But now let's try to see this from a slightly different way. Okay. So let's construct this trivial nuking optimization problem by minimizing like a dummy variable y subject to the condition that y is equal to x. Okay, so we know that the optimal solution is simply norm of x, right? Now let's apply the same machinery that we've been using for the beginning part of this lecture and construct the Lagrangian. So we get this, we move like y to the other side, and then add this Lagrange multiplier variable with u transpose x minus y, and then we can decompose the two things in to get these. Okay, and in order to construct the dual, and then we need to minimize this over the variable y. Okay. Okay, so this term has nothing to do with y, so we are left with just this term. So notice that whether this term have a minimum really depends on the choice of u, and by definition of the dual norm, like suppose u has a just a Holder's inequality. Like suppose that the dual norm of u satisfies that the dual norm is larger than 1, then we can always choose y by simply make y as large as possible towards the direction of u. Then we can then we can shoot everything to negative infinity. Okay. On the other hand, I suppose the dual norm of u is smaller or equal to 1, and then we know that the minimum of this quantity is equal to 0. Okay. So you can also see this from the Finchu conjugate, right? So notice that this is a minimization over y is a conjugate of the norm function, which gives the indicator function on the dual norm. But then now let's construct the Lagrange dual. With this additional constraint, then the Lagrange dual is simply the max of u transpose x subject to the dual norm constraint. And that checks the definition of the dual. And by strong duality, we know that the optimal solution of this is equal to the optimal solution of this. Therefore, x is equal to the dual of the dual. Okay. Let's give another example. So in Lasso, in Lasso, we often like so previously, like we've talked about using a different reformulation by adding a dummy constraint of that looks like u is equal to beta, so that we can replace this with u. So now let's do it in the slightly different way, so that we can make some sense out of the dual formulation of Lasso. Okay. Like there are different ways of doing this, different ways of applying the reformulation to get the dual of a non-smooth optimization problem. So for Lasso, we can do this. We can alternatively do the reformulation by getting rid of the difficult part that comes with x. Okay. So if we replace x beta with z and minimize over beta and z simultaneously, Then we construct the Lagrangian. We minimize the Lagrangian over the primal variable. Okay, and since this is a since this is now a problem that's more easily solvable, we can first get rid of the z, since the non-smooth term doesn't really depend on the z. So we can work out the gradient corresponding to z, which gives us z minus y is equal to plus u is equal to 0, right? And then we can substitute. Then we can substitute the fact that z minus y is equal to 0 into the first term. Z equals to y minus u. Okay, z equals to y minus u gives us this, and then u transpose multiply with z gives us the other, and then we can get this term, and then we can also take the subgradient with respect to beta, and then find the corresponding parameter of beta. So notice that the terms that associated with beta is only lambda of beta 1 norm plus like a linear term in beta. So this will be x transpose u transpose beta minus, and we want to minimize over beta. So notice that what is this again? This is a Finchel conjugate. So we can take the Finchel conjugate of the norm, which is the indicator function on its dual norm. Okay, and then plug in this x transpose u over lambda into here. Then we get an indicator function as part of the dual problem that we want to maximize. Okay, collect everything together. So notice that this is just a constraint, right? And this term is a quadratic function in U. Let's drop the part that's independent to U. We can drop the part that's independent to U. So this one goes away, and then we can change the maximization to minimization, and this essentially becomes a projection problem. So we want to find the closest point within this convex set that the input y is true. So we want to optimize over U. And then just project y to this set that's carved out by this x by this box constraint on x transpose u. Okay, so it's easy to check that Slater's condition is true by simply taking u to be 0. Okay, therefore the strong convexity is true. However, yeah, notice that when we say that these two problems are equivalent, it doesn't really say that the optimal solution, the optimal objective criteria is also retained. So this is something that we need to be really careful about. So the optimal solution, the optimal criteria is obtained when this constant is there. But after we remove the constant, then we no longer have that property, even though the two problems are identical in nature. Okay, and suppose we can solve these projection problems more efficiently, then that gives us an optimal solution U, and we can use it, and by the KKT condition that we had before, we can use this to construct the optimal solution by simply optimal solution beta by simply solving a linear system of equations. Okay. So notice that notice that if we move y to the other side, okay, so U is actually just equal to y minus x beta. So this is a residual. This is what residual. This is a residual. This is a vector of differences from your prediction to the actual label. Okay, so that assigns meaning to the dual variable as well. So it shouldn't be surprising to you from the way that we're reformulating. So we're simply taking z to be x beta. That's the prediction. and then naturally the Lagrange multipliers on this condition should have something to do with a gap between y and z. Okay, geometrically, like what does the projection problem look like? So you can think about this as follows. And at the solution beta hat, u hat is the residual between y and x beta. Okay, so this is a difference. And if you project y to this convex polytope, and you like this point, I guess this point is u. So this means that if you take the difference between these two, and this vector is simply x beta hat. Okay, and if we convert everything by just doing a rotation of the space, by just doing a linear transformation of the space, by taking the x transpose inverse, so you can do this for every single point in the geometric space, and that converted this L infinity norm ball into something that's just a hypercube. Okay, and essentially by doing this rotation, then this y becomes somewhere else. So that's one way that you can think about this reformulation of taking z to be x beta. So that's a transformation of everything in the space while retaining the same property of the problem itself. Okay. As we have seen in the previous examples that deals with working out the dual variable and solving the minimization problem from the Lagrangian, it is closely related to the problem of conjugation and the conjugate, the Fincher conjugate definition of F star. So specifically, the kind of problems that we often run into when deriving the dual involves a minimization problem of this form with some convex function and then with some additional terms that are coming from the added terms from the dual variables or the Lagrange multipliers. Okay, so take the problem of this form that you are trying to minimize like two objective functions at the same time. You are trying to minimize the sum of these two. Okay, you can reformulate it into fx plus gz and substitute an additional trivial constraint x equal to z. And by doing this, we can lift this constraint up into the Lagrangian and then solve each one of these problems separately. And that allows us to write the dual form into simply the Fincher conjugates of U. Okay. Okay, so it's still the same problem that we want to minimize the two things with the same variable, but then one problem is related to another. So this is like one of the ways that you can get the dual problem for unconstrained optimization problem. Okay. And sometimes as you do the conjugation, as you suppose some of these are norms and non-smooth terms, then the constraints are going to be directly encoded in this conjugates F star and G star. So the example that we gave are when this G is one norm, then this G star would say that this U needs to be in the L infinity norm ball. Okay. Or if there's a lambda here, then correspondingly this U needs to be smaller than lambda. Is it lambda or 1 over lambda? So now I'll leave it for you guys to work out. Okay. So in this case, like when you have when you have indicator functions, then when you have constraints or indicator functions in the primal, then we can apply the previous trick of adding a dummy constraints and introducing variable z by decomposing these two, and that allows us to write the more general dual for the constraint optimization problem. Okay, yeah, with this norm as an example, that's typically seen. Okay, so so we talk about Lagrange dual and the KKT conditions. It's not the only dual that appeared in the literature for convex optimization problems. There are also the Finchel dual that's very popular. So you can actually get Finchel dual from Lagrange duals directly using the same trick that we've seen before. So the only difference from the trivial example now in the Finchel duality problem is when is that the input to this function g is subject to an additional affine transformation. Okay, so instead of defining x to be z, so let's define ax to be z. So we get a cleaner looking form in the dual. So if we do that and then construct the Lagrangian, so we'll have x fx plus g ax plus u transpose ax minus z. Okay, and then let's separate this into u transpose ax minus u transpose z, and then as we minimize simultaneously over s and z, this problem decomposes, and then we can write the minimizer of this term to be the negative of the Finchel conjugate with a transpose u substituted into f star, and this term is easier than we just get minus g star like minus u. Okay. So one thing that I want to point out is that so previously this linear transformation, so that's sometimes where the difficulty is in the optimization, has now been transformed from functions related to g into functions related to f, right? So now in the g star function, this becomes u without a linear transformation, and the a transpose now appear in the f part of the problem. Okay, so so this is a slightly more general form of lasso. That's called when this norm is one norm, this is called the generalized lasso, and f is their loss function, and there could be other kind of structured penalty that we want to induce. So one example of this would be to say the sum of xi minus 1 absolute value from 2 to n. Right, so this is related to the total variation denoising problem that you have seen in the first homework. Okay, so you can convert this problem into something else that doesn't depend on this one norm. So specifically by the primal and dual relationship of this using the Finchel dual, you can derive that the dual problem is something that resembles the projection problems in a different space that's transformed by f, subject to a very simple constraint that this u star is smaller than 1. In particular, in this example, so this can be written as some difference operator multiplied with x, dx one norm. If you do the transformation, the d will be on this side, and this becomes the L infinity norm, norm ball, which says that this is smaller than 1. So notice that if we do projected gradient descent on the primal, so this is the non-smooth term that we need to deal with, and solving such structured non-smooth term is not necessarily easy. Right, so it happens that for this problem it's actually easy, But in general, like when you have A of X, then the prox with respect to A of X, like may or may not be efficiently solvable. But once you do this transformation, so as long as F is smooth and differentiable, then you can do the proximal gradient descent or the projected gradient descent of the dual, and then projection onto the L infinity norm ball is trivial. It simply involves clipping every coordinate such that every coordinate is smaller than 1. Okay. So let's talk about more duality. So so remember that the most general form of the convex optimization problem that we've learned is the conic programs, which subsumes both the LP, the semi-definite programs, and essentially all the convex optimization problems that we talked about. Okay, so there's a dual norm. There's also dual cone, right? So for any cone, let's consider a vector space R to the n. It doesn't necessarily doesn't necessarily need to be a convex cone. Just any cone. We can define the dual cone to be the set of all y such that y transpose x is always positive for all x that's inside this cone. Okay. So no matter what you do, so even if you set this dual cone to be a non-convex cone, so something that looks like this. Okay. So this is K. You can always when you figure out what this K star is, the K star is always a convex cone. Okay. So so in this case, the K star actually is so let's say that this is the part that's perpendicular to this, and this is a part that's perpendicular to this. And in order for the direction to be positively correlated with anything that's inside this cone, then this is the boundary that the dual cone needs to satisfy. And moreover, we can do the same thing. We can do the same thing here. And now if this is a right angle, and then that will be the direction that that this hyperplane needs to satisfy. And intersecting with the other one, then we end up getting that this is a region of the dual cone. So this is what we call the K star. Okay, so okay, so we can see that this is always convex by using by using the fact that this is an intersection of subspaces, intersection of half spaces. Okay. Moreover, like there's a property that if you take the dual, just like the dual norm, if you take it twice, then it recovers the same same cone before. Let's give a few examples of the dual cone. So if we consider the linear subspace, then the dual cone requires that any point in this dual cone is like non-negatively correlated with all the points in the primal cone. Then this essentially require everything to be 0, because the subspace you can multiply that with both +1 and -1, and it remains within the subspace. So this is saying that the dual cone of a linear subspace is actually is orthogonal complement. And the dual cone of the norm cone, or often the second order, the second order norm cone happens to be the norm cone of its dual norm. So specifically, recall this picture that we drew in the lecture 2 when we talk about convex set and convex functions. If if this is L infinity norm cone, then that looks like the section looks like this. This is a box, and then there's another box. Okay, so if we consider all the supporting hyperplanes of this L infinity norm cone, then you see that the supporting hyperplanes like you see that the intersection of the hyperplanes that satisfies that y transpose x larger than 0 would carve out a cone that looks like this. So it becomes the little square that's always in the in the middle. Okay. So there's interesting property when we apply this result to semi-definite cone, because the semi-definite cone is self-dual, and it's easiest to see that algebraically by simply applying the definition of the dual cone. So the way to see this is the following. So if we want to see this direction, then we simply take the eigen decomposition of x by decomposing x to be q lambda q transpose, and then using the property of the trace, we have trace of y q lambda q transpose is equal to trace of q transpose y q lambda. Without loss of generality, since this x can be anything, we can take x such that this lambda is equal to 1, or we can simply take this lambda to be strictly positive, and then saying that this is larger than 0 is equivalent to say that the trace of q transpose y q is larger than 0. Okay, but we can also choose q arbitrarily, since this is for all x larger than 0. We can choose q to be an arbitrary orthogonal transformation. So let's choose this q to be the one that diagonalizes y. So once we do that, this becomes the if we do that, then this becomes the trace of the diagonalized lambda y is larger than 0. So that alone doesn't gives us the fact that y is a positive semi-definite, but then we can keep choosing this q to be different things. We can choose like several different q's, so that we end up getting this inequality for arbitrary combinations of the eigenvectors of this y to be greater than 0. By simply choosing this lambda parameter, to select the different eigenvalues, and that allows us to show that the lambda I of all the y is larger than 0, which checks the condition that y is a positive semi-definite. Similarly, from the other direction, you can take eigen decomposition of y, and then you can take eigen decomposition of y, and yeah, the other direction is actually easier, because it simply follows from the fact that for any vector y transpose y, this is larger than 0, and then that implies that for all the positive semi-definite x, the trace of yx is always larger than 0. Okay, so we talk about the conic programs are the most general convex optimization programs that, and then by simply applying the Finchel duality, we can get the corresponding dual problem for the conic program, and that involves that involves the support function of this cone. Okay, so and in fact, when k is a cone, then this is simply again a constraint that u is in k star. So where k star is a dual cone of k. So remember that when we talk about the Finchel decomposition, that's when we talk about any x can be decomposed into the prox of f x plus prox of f star of x, and this is where we gotta apply this again. So notice that when this f is when f is an indicator function to a cone, then the corresponding prox of f star is a projection to instead of its dual cone, it's a projection to its so-called polar cone. So we'll see this in the next slide. Okay, so we talk about the dual decomposition. Prox of prox of f star when f is an indicator function to this set which has a spanning cone, or to this cone, it's simply a projection to its so-called polar cone. So polar cone and the dual cone are closely related to each other. The only difference is that they're directly opposite to each other. One wants this to be larger than 0, and the other one y transpose x to be always smaller than 0. Okay, so so I guess the last couple of slides is a little bit of revisit of the convex analysis part of the lecture, and it connects us back to when we talk about the proximal operators, when we talk about the cones and the corresponding subgradient. And the purpose of these is that even though the KKT condition and the duality, the Lagrange duality, appear to be something that's completely a new kind of beast, it is actually still something that can become completely described using things that we've learned before from the convex analysis. And Finchel conjugates remains like very useful in these cases, and it helps you to do your calculation faster and easier, and sometimes it gives you interesting insight that informs you on how to design better algorithms to solve those problems. Okay. So before I end today's lecture, I wanna say this again, that since since we can reformulate mostly the unconstrained primal problems in various different ways. So depending on how you reformulate this problem and introducing different dummy variables, you'll end up getting like very differently looking duals. So there isn't a single way of doing that. Even for the problem as simple as Lasso, we've talked about 2 different ways of doing that. Okay, so some reformulations might lead to more cleanly looking dual that have interesting geometric representation, and some other reformulation might have another type of dual that's not so clean, but they also have a different set of geometric representation. Okay, So when you have a problem yourself, my suggestion is that since it is not too difficult to derive the dual, just try like multiple approaches. So maybe you like one way better than another. Maybe there's some insights that are more easily seen from one way of reformulating the problem than the other way. Okay, and now that you've get the art of deriving the dual and stating the KKT condition, and hopefully this calculation become pretty straightforward and pretty mechanical, and you can do it multiple times without without wasting your entire afternoon on that. Okay, so like we've talked about this before. In general, when we derive the dual of the dual, then sometimes we recover the primal, and this is really the case if we do not do like any additional reformulation in the dual space. So sometimes when you have a primal problem, you make it a dual, and then you reformulate it into a slightly different dual that's equivalent, such as subtracting constants and so on. And then in that case, once you get the primal, and the primal tilde may or may not be the same. Yeah, sometimes this has interesting properties. I can point out a paper that actually uses this trick to reformulate the problem so that you get something that's more easily solvable. Okay, but suppose you stick with this and then derive the dual of this dual, then what you end up getting is always the primal the primal problem. Okay, you can prove this more formally for this setup problem with linear constraints. Okay, the same kind of observation were made in the Rockefeller book involving talking about conjugate of so-called bifunction. And this kind of observations that the dual of the dual is a primal holds more generally for nonlinear inequality constraints, but it's more complicated than the one that we talked about just now, which you can directly prove using the tricks that we learned today. So the last slide is only for those who are interested in knowing more details about bifunctions. Okay, that's the end of today's lecture. Yeah, I'll spend the next 5 minutes to answer questions in case there are anything that you guys wanted to ask about today's lecture. All right, if not, enjoy the homework.